Thank you for the kind introduction. I appreciate that a lot. And I'm going to curb a bit of our enthusiasm about AI and machine learning in this talk and try to ground the discussion more in terms of, yes, it is important, but how do we get it right? So I don't think I need to emphasize a lot here, which, in the lives, our lives in the post-pandemic era is heavily dependent on all the internet services. Not that it was not the case before, but it is the reliance is even more intense now. And it is ever more important to make sure that everybody has access to secure and performant internet. And it's a very critical goal. And when we think about this as the goal, then we have to start thinking about who's going to make it work, right? And the first thing that comes to our mind is all types of different service providers out there, either the one that are providing the cloud or content services or the internet services, also the enterprise networks as well as the community networks, right? And all of these enterprises and all of these service providers are interested in making sure that the internet services are secure and performant, right? But they have constraints that most of them are dealing with limited infrastructure and operational resources. The motivation for some is profit, that you want to minimize the amount of infrastructure and operational resources you spend, and for some it's just the upper limit of how much resources you have access to. And if that is the goal, I think we have made significant progress in last 1 decade. I'm referring to software-defined networking, which enabled us having programmable data plane in the network. What it truly enabled was that it enabled us better telemetry data that provided us better insights into what's going on in the network. There, we could just plug in our analytics pipeline, extract insights, and have a much better understanding, in-depth understanding of what's going on in the network. And then we could react with some precise controls as well. Like if you identify some traffic, which is, like running a DDoS attack on your network, you can go ahead, drop that traffic in your own network or drop that somewhere upstream. So essentially, what SDN enabled was very effective network automation, which is that it was making sure that we're able to keep our networks secure and performant with limited set of resources. And that's the kind of like goal that I was talking about. So there is a lot of progress in 1 decade, right? But still, when we think about the SDN service or the SDN-enabled infrastructures, the SDN's network automation is still human-centric. What I mean by human-centric is that we still rely on a lot of pre-existing heuristics and rules to figure out, like, when we see something, what is our reaction going to be, or how are we going to identify certain events of interest in the network, right? This works well if the events that we are interested in are relatively simple, easy to identify, don't change too much over time, right? But this is, as we know, is ineffective against events or network events that are dynamic, coordinated attacks, multi-vector threats that are coming into a network. And as we know, we have witnessed that APTs are a big challenge, advanced persistent threats, where your network gets infiltrated and there's lateral movement going on in the network. The attackers are just keep on evolving over time. It's really hard to catch up, right? But more importantly, there is another development that has been going on, I would say, for the last 1 decade. And this was articulated by the report that came out by National Security Commission on AI. What it talks about is that, this whole excitement about AI is good. AI can be very transformative for our society, but it's a dual-use technology, like everything else, right? What it really means is that it can empower us to, say, make our networks more performant, do all the LLM stuff that we're talking about. But that AI can also be used by malicious actors to threaten our digital societies, right? And this, as we are already witnessing, this AI-enabled tool are getting more and more the first resort in the new era of conflict, right? Where there is a state-sponsored activities going on, the malicious intents are state-sponsored, and there is a lot of threat to our digital societies now. But something that really caught my attention, and something that we have been communicating in the community for past 1 decade, is that trying to counter AI-capable adversaries with just human intelligence alone is invitation to disaster, right? So what it really essentially is motivating is that, if we are trying to fight this AI-powered threats with human intelligence alone, we are making our digital systems much more vulnerable to different type of threats. And this is a very compelling case for complementing our human intelligence of running networks, operating these networks with AI, right? Now, when I say AI, it's a very abstract term. What does it really mean, right? When we say about AI in terms of networking, what does that really mean? So what I really mean is that we have SDN, we have these like predefined set of rules or heuristics in place that are closing the loop in terms of monitoring what's going on and taking actions along that. But how about we replace that with bunch of different machine learning agents or machine learning models out there, which are doing a good job of identifying those complex, subtle patterns in the traffic and figuring out or synthesizing the actions that need to be taken, right? And we have been referring to this as self-driving network, right? So this has been articulated in the community for at least 1 decade again. It's like, we can think of building a network that is capable of running itself, making sure that the networks are secure and performant with as little human intervention as possible, right? Whatever we are doing right now with network automation is already a step in that direction, but it is, as I said, it's not capable of making or handling complex issues out there, right? And when I talk about this self-driving network, as you can see, the most important requirement that we have is the need for machine learning artifacts that are ready for production deployment, right? So machine learning artifacts, when I say production deployment, what does it mean? That these models should be generalizable, which is like, they should perform as expected in the target settings where you want to deploy them. We should have some confidence in their robustness. We should have some trust in their decision making. We should know that they're going to operate as expected, and we should know where and when they're going to fail, right? So this need for having a production-ready machine learning model is important. And I want to emphasize that it's not just one model that's going to work, right? If we want to realize this goal, we need a lot of them out there, right? Now, we should feel confident as a community because we have invested around a decade or more than a decade building machine learning models for networks, right? It's not a new topic. It has been going on. I would say it's as old as networking. People have always been thinking about how we can offload the decision making to some automated algorithms out there. And machine learning has been a tool that people have explored, right? If you search around, there are at least 1,000 plus, and maybe I'm underestimating, there are at least 1,000 publications out there that talk about machine learning for networks, right? And there are multiple products and startups out there. Billions of dollars, both from the government and VCs, have been invested in this space, right? So given all this investment of the community for past 2 decades, what is our expectation? Our expectation is that if you come to me and tell me, here is my problem, here is the environment where I want to deploy the machine learning, it should be very easy for me to train such a model that is going to work as expected in those settings, right? And I should have not just one, but a lot of machine learning models out there that are ready for these deployments, that are ready to an extent that I have confidence as a network operator to deploy them in high-stake decision making, right? So this is the expectations that we should have, given that we have invested so much, right? But I'm sure that most of you have now figured out what I'm going to say next, which is reality is very different from what we are expecting here, right? So we do not have machine learning models that are out there ready for deployments right now. The availability of public data set, which is like what data set is available right now, is dictating our choice of what problems we are going to solve and what environments we are going to focus on, because we don't control what is the right data for a problem. We are looking at what is the right problem for the data that we have, right? And there is abundance of machine learning artifacts. Don't get me wrong. There's a lot of research that has been done. There are a lot of machine learning artifacts out there. They do really good in lab settings, right? And when you take them out, deploy them in any production settings, if you have tried that, you will know none of that works, right? Or most of them don't work. And as a result, network operators have been excited about it, have tried it. And then when things have failed miserably, there is this growing reluctance that when a lot of network operators get irritated when I say, oh, I want to do machine learning for networks, right? Nobody is really excited about machine learning for networks for people who really care about the security and performance of the network, right? So overall, what I'm trying to say is that, what we really need is that we need a lot of machine learning artifacts that are ready for production deployment. What we really have is that even getting one single machine learning model deployed in production settings is hard. Right? So why are we here? We are a bunch of smart people out there. This should be easy, right? Why are we here? Why are we, after investing so much of time and resources, why are we here that we don't even have confidence in one model to be deployed in production? So let me talk about some of the fundamental roadblocks that are stopping us. So one big roadblock is that when we think about developing machine learning models, what we have done is that we have adapted standard machine learning pipeline that was working fine for different other domains, right? What this standard machine learning pipeline expects is that when you are using it, you know what is the right data, right? So the onus of figuring out what the right data is on you, right? And, we are all, we have good intuitions. So we think that we know what is the right data, but that there is no feedback coming to me whether it was the right data or not, right? So whatever we feed in is coming out as the model, right? So if we feed in garbage, the garbage comes out. And that's most likely what's happening. So if you are going to use machine learning, you really have to answer this question that for a given problem, for a given target setting, what is the right data to use, right? Okay, this is one problem. Now talk about another. When we talk about machine learning for networking, we typically talk about supervised learning techniques. Supervised learning techniques require labels, right? So where are the labels coming from? Either you go to your production network, collect some data, but labeling some pre-existing data is hard for any problem. Like maybe for one or two problems, you might be able to do it, but in general, labeling is hard. So what most people end up doing is that they do this endogenous data collection, right? So for a specific problem, they collect and generate their own traffic where they know intrinsically what the labels are going to be. And that's what they use for machine learning. So now there is this additional step of data collection. So when we think about machine learning for networking, we also have to think about data collection. So now we don't only have to answer what is the right data, but we also have to answer how are we going to collect the data, right? And now let me highlight the challenges that we have when it comes to data collection. So data collection is not easy. Right? As Casey was pointing out, data collection is hard. People have tried that. A lot of people have been trying that. But when it comes to data collection for machine learning and specifically in context of networking, the efforts are very fragmented. That everybody talks about collecting data, so they only think about one problem and one or two types of network environments from where they want to collect data, right? And there is little extensibility from one effort to the other. So if I want to collect data for a new problem, given that some data was already collected for another problem, the extensibility is very limited. So what really ends up happening is that we end up, the threshold of collecting data is very high. So we end up if I want to start on something new, there is no data. There is a lot of effort. My PhD student probably would have exceeded 2 or 3 years limit before I start collecting some meaningful data. So I end up using the data set that already exists, right? And what it really means is that now, for the problem that we want to solve, we are not thinking what is the right data. We are just thinking for the data that already exists, what is the right problem? What is the best model that I can use, right? And this is, as you can imagine, is a bit regressive thing, and maybe one reason why we are not making as much progress as we want to, right? Now, there is one more block here. The thing is that when we rely on this standard machine learning pipeline, the way this works is that it will pick the best performing model for you, right? You have flexibility in terms of defining what is the loss function that you care about and what is the optimization definition for you. But at the end of the day, in most cases, the models that work great are black box models, right? So you don't really know how they're making the decisions. So when you see great performance in the model that you have trained, you have no idea whether this high performance is attributable to the model really capturing the causal structure of the problem, or maybe the model was just underspecified and it picked one of the many random possibilities of models that were out there, right? And now this term might not be very familiar to you, underspecified. What does underspecified means, right? So there is this whole class of underspecification issues that are troubling and affecting the generalizability of machine learning models in general. It just does not affect the networking area. Like any area where machine learning is being used, underspecification is a big threat, right? What it really means is that when you were training the machine learning model, you couldn't really provide all the information that was required to come up with one best model that is capturing the optimally capturing the causal structure of the problem, right? So this lack of information was there. And the artifact of that is that the models that you train are either vulnerable to shortcut learning, which is that they find some shortcut in the data and give you very high performance, but then those don't generalize, right? Or you have this OOD issue, which is their models don't generalize for out of distribution samples beyond the training data that you have. And finally, there is a condition called spurious correlation, which is that you were able to find some lucky guesses, make some lucky guesses and find some coincidental relationships, but they had nothing to do with the causal structure. All these things will mean that if your model is vulnerable to any of this issue, it will give you great performance on the training data, but it will not really generalize, right? So let me try to make this discussion a bit more concrete. So suppose that your goal is to solve this HTTP brute force detection problem. As most of you know, that this is typically the first step that the attacker will take to infiltrate your network before it will do the lateral movement inside your network, right? So this is a very important problem. Now, if I want to solve this problem, and what is the data set that I have? Assuming that data collection, we just internalize it, data collection is hard. So let's pick what data is available for us. So this CIC-IDS is something which a lot of people use. So this is a data set that was curated by an organization in Canada, highly used. I think there are at least hundreds of papers that cite this data set. Now, the question is that I don't know if this is the right data, right? Depending on where I want to deploy it, depending on the complexity of the problem that I care about, I don't know if this is the right data, right? But not only don't know the right data, the model that I've trained, it's giving me F1 score of 0.99. That's very blinding, right? So I would think F1 score 0.99, how bad things can go, right? I would think, this is good, this is right. But technically, I don't know if this great performance is because of the underspecification issues, right? And if by some magical things, I'm able to figure out how the model is making decisions, and I figure out all the decision making is based on just one feature, which is the TTL value, and implying that this is a learning shortcut that the model truly learned, I don't know how to fix this problem, right? Because I didn't curate that data. So I don't know what is the better data, and I don't know how I'm going to get that better data, right? So this is where we are. And answering these questions is very, very critical when we talk about developing production-ready machine learning artifacts for networking, which are, as I said, are very critical for the self-driving network that I'm talking about, right? So in this context, what is that we are doing, right? So we argue that all the infrastructure that are out there with the best intuition as a domain expert, you can think of what is the right data to the best of my intuition. So you start with some data, but let's not make that the final data. Let's start with some data, right? Then we go and augment the standard machine learning pipeline, adding some steps of explanation and analysis. So I don't reason about when I get a good F1 score, I'm just gonna deploy that model. I'm going to explain and analyze how this model is going to make decision. Then I'm going to bring my domain expertise and reason about is this how things should work? Or there are some obvious flaws. Can I identify some under specification instances in the data? And can I map them to the problems in the data itself, right? So problems in the models map to the problems in the data. And then can I then go back and refine my intents to collect the data? And if I do that iteratively enough, I might be able to, with each iteration, figure out or fix some under specification issue, improve the quality of data. And with multiple iterations, maybe I will be able to fix the under specification issue, collect better data, and provide better opportunities for the model to generalize, right? So what I have been doing for past few years is trying to develop some building blocks for this closed loop machine learning pipeline. So starting with this infrastructure that is called Pineo. So the main argument that we had is that, if you are a researcher sitting in academia, the first thing that you need is data, right? So either you use all the infrastructure that, Casey was talking about, or you go to some industry and say give me your data, right? That's very hard. So the argument that we had was that, okay, let's try to start thinking about what can we do in academia. We have one production network, which is our own campus network. So how about we transform our own campus network into a data collection infrastructure, right? So we did a lot of work in terms of how do we transform your own production network for data collection. So we start with some data there, right? And then for explaining and analyzing the model, we built a tool called Trusty. So Trusty, what it does is it helps us explain and analyze the model's decision making, right? So we can reason about what type of decision making is going on, how it's making decisions for all the data points or majority data points, and is there an evidence of under specification for me, right? And then as a domain expert, I can go back and refine my intents, but I still need to collect data. I need something to collect the data, right? So we built a tool called NetUnicorn. So what it enables is that it lowers the threshold of collecting data for any learning problem from any type of environment out there, right? So I'm gonna just talk a bit about these efforts in a bit more detail, starting with Trusty. Now, what is Trusty? Trusty is a post hoc global model explainability framework. What does that mean? It means that you can train whatever model you think is best for the problem that you're working on, right? So we are not challenging your domain expertise. You can use that expertise. But once you've trained that black box model, you put that as input or provide that as input to Trusty. And Trusty is going to generate explanations for your model's decision making. Those explanations will be in the form of decision trees. And we wrote the whole paper about how we are going to make sure that those explanations are agnostic to the architecture, the specification of the model that you have. It is offering high fidelity, means that the decisions that you see in the explanations are matching the decision that the model is really making. And then it is low complexity, which means that as a human experts, we really want to make sure that we don't throw you thousands and thousands of decision rules. We try to minimize the number of decision rules that capture the causal structure of the problem more effectively. And then the explanations are, of course, stable, that every time you run the tool, you don't end up with new decisions or new explanations, right? So we make sure that the explanations are stable, right? So we have this as a paper at CCS last year. For more details, you can read that. But I'm going to talk more about, not about how it works, but more about what it enables, right? So I am going to revisit the problem that I was talking before, which is detecting the brute force attack thing, right? So I use the standard machine learning pipeline. I use the CIC-IDS dataset. I use multi-layer perceptron as the model. I get an F1 score of 0.99, right? Now I can use Trusty and input this black box model to the Trusty and also provide the dataset that it used for training. And what it will give me is the explanation of how the model is making its decision. And what we see here is that it is telling me that majority of discrimination between what is malicious and benign is done based on the TTL value. Now you might wonder, what does TTL mean in this case, right? TTL is basically an indication of number of hops the node has taken from the start to the end, right? So end here is the target node. So what it really means is that the data set is such that all malicious hosts have one type of TTL value, the other have other type of TTL value. We dig into the data a bit more, how the data was collected, and we realized that the way data was collected was that all benign hosts were in one subnet, all attack hosts were in another subnet, and they had distinct TTL values, and that was the only thing that the model was learning, right? So you could be blinded by the fact that the F1 score is 0.99 or sometimes even 1.0, but in reality, model learned nothing. It just learned how to cheat, and it just figured out a shortcut that existed in the data. And then, if you try to put this model somewhere in the real world, this is not the TTL distribution that you expect, and the model is just going to fail miserably, right? So this is just one example. We tried to understand how the decision making is going on for a bunch of other problems and state-of-the-art models and different type of public data sets out there. So detecting VPNs and anomaly detection, fingerprinting, OS fingerprinting, device fingerprinting, and all these different type of public data sets that people, especially in the network security community, were using, and the state-of-the-art models which were claiming that they had the highest possible F1 scores and performance and so on and so forth, right? And what we understood was that most of them were some type of under-specification issues, right? So some of them were learning a shortcut, some of them were overfitted to the training data, some of them were learning some coincidental relation or the spurious correlation, but almost nothing was free from these under-specification issues, right? And we kind of also indicated that all of those issues were attributable to the nature of data set that we were using, right? So the data set that were publicly available, people, as I mentioned earlier, researchers are forced to use these type of data sets, and all of these data sets have problems, right? So how do we, this whole process provides us insights into, okay, there's a problem, right? But we can't just go about and say oh, there's a problem, there is a problem. We need to solve the problem, right? So how do we solve the problem? This problem is something, the under-specification issue is something not new for networking or machine learning. People have been talking about this issue for a very long time. And there are solutions that people are exploring. Maybe we should find some better representations for the data. Maybe we should improve how we are training the model, testing it. And most importantly, people are saying we should use different data set, right? But when people talk about different data sets, especially in context of other domains, they're talking about passively augmenting the existing data, right? So you have some data, you have collected some data, but now you just passively manipulate that data so that it provides you better opportunity to generalize, and it's not vulnerable to obvious shortcuts and other under-specific issues, right? But this, as you can notice, this is not something which is going to work for networking. You cannot just collect packet traces and then passively augment things within that packet traces, right? That's not how network works. A sequence of packets that you see in network is manifestation of different layers of protocol interacting with each other and interacting with the environment itself, right? You cannot just do passive manipulation network data. And more importantly, if you go with whatever everybody else was doing before, you miss out on the opportunity that we have made so much of progress in trying to explain the model decision making, right? So now we understand better what the problems of the model were, right? So how can we leverage all this information to do something better and fix this problem, right? So as I briefly mentioned before, our approach is that we use the insights from Trusty, which is you provide us some explanations and analysis of how model is making a decision. Then as domain expert, we can go back and refine our intent to collect the data. And hopefully, if we do this iteratively enough, we would be able to move forward from what data we started with to something which is better, providing model better opportunities to generalize, right? Now, you might see some irony in what I'm saying here. So what I told you before is that collecting data is hard. Now I am telling you, you not only need to collect data, but you need to collect that iteratively, right? So I'm countering myself, challenging myself, because even one-time data collection is a hard thing because of the fragmentation problem that I'm talking about, right? And now I'm saying you need to do this for every problem, you need to do this in an iterative fashion so that you get the better data. How are we going to do that? How do we simplify that, right? So what we think or what we propose was that, if we really want to solve this problem, we need to think about how do we build the thin ways for data collection, which is one platform, one solution that helps you collect or enables you to collect data for different type of learning problems from different types of network environments, right? So if I want to focus on problems that are specific to campus network, wireless part of the campus network, I need to collect data from that part. And then for a different problem, the same problem, but from a different environment, I should not be thinking about redoing the same thing, right? And focusing on all the redundant tasks of how I collect the data. But if I can have some platform that simplifies doing all this for me, that would be great, right? This sounds fancy, and if it was so easy, we would have solved that a decade ago. That was the goal that we set ourselves up for. And in response, what our approach was that, like this whole problem is because the process of collecting data is very monolithic, right? So you have to worry, when we talk about collecting data, you have to worry about expressing your intents, which is what data you want to collect, from where you want to collect it, but also the mechanisms, right? And these are all intertwined with each other. And that is what affects the extensibility of data collection effort from one effort to the other, right? So we said, let's start with some type of disaggregation. Let's start to disaggregate the intents, which is like what you want to collect from and where you want to collect it from how. How are you going to do that? Let's not put that onus on the users. Then we further focused on disaggregating the intents, that we need to decompose the intents into independent reusable pipelines and tasks. Which what it means is that if we can break down the intents into these pipelines and tasks, it provides us extensibility across different type of learning problems. And then we were able to also argue that we should, when we think about these intents, we should not think about where these intents have to be realized. So we need to provide some decoupling there as well, right? So for example, if I write some workflow of how I'm going to collect data that I'm say maybe work on a private network or on a virtual network in my laptop, I should be seamlessly able to put that same workflow on a production network out there as well, right? So this is what we mean by disaggregation of intent. And of course, the mechanisms of how I am going to deploy the intents that I have, how I am going to handle all the runtime issues. As a user, we should not be worrying about that, but we should also be making sure that we are breaking them down into smaller set of services that are modular, that we can keep on iterating and adding over time, right? So what we ended up building was a platform, NetUnicorn. It is a data collection platform. It takes in the intents expressed using programming APIs that we provide and provide that to the set of core services that NetUnicorn provides. And then this core services are translating those intents into a bunch of instructions that different deployment systems can understand. So we are, not fixating on a specific type of infrastructure that we are going to use. So whatever interface the infrastructure is providing us, we can interface with that. Like in some cases, it's like Kubernetes, if it's all the container stuff. And if it's a physical SSH-based connection, then we can use SaltStack and so on and so forth. So it translates those instructions for these deployment systems, which then interact with physical nodes or virtual nodes that you are trying to use for data collection. And then this services also handle the runtime issues, right? So let me show you how this API that we have developed can be used for collecting the data for the problem that we've been discussing so far, right? I want to collect data for this problem where I want to mimic some type of attackers, some type of benign host, and some type of target, right? So I will pick 3 different type of abstract nodes from 2 different type of infrastructures. Like one, assuming that the server is hosted on cloud, and then there are these attackers and benign hosts that are from my own campus network, right? And then I can define 3 different type of workflows for each categories of hosts, which is like, if I'm the target server, you just start the HTTP server and do packet capture, right? And if you are the attacker, then you take some break and then use this tool called Patator, which is used for brute forcing. So you start that tool, right? And if you're using, if you're the benign one, then you just, use the valid credentials and log into the server, right? And then once I have that in place, sorry, I think, but I think, once I have this workflow refined, I can just map the nodes and pipelines with each other and say dot deploy, dot execute, and then the experiment will run. Like on all the core services will take care of it, and then the experiment will be complete and the data will be available to you, right? So overall, what NetUnicorn is enabling is that for any given learning problem environment, it simplifies expressing data collection intents, right? And what essentially it means is that from here, what is the state of the art right now, we can achieve this, which is like, a thin data collection baseline, which enables collecting data for different problems from different type of environments. So, overall, what I've been talking about is that NetUnicorn and Trusty together, they are helping us realize this closed loop machine learning pipeline, right? Now, the next question is that, does it really help iteratively collect better data, right? So, I'm saying that if we do this iterative enough, we might be able to solve the problem, right? But does it really work, right? So let me dig into this example one more time and say that let's think about iterative data collection. We start with the same problem, but now my goal is that I have resources on my campus network. I've transformed my campus network into something which can be used for data collection. So I want to collect data from my campus network and deploy it in some other target setting, which is say the cloud setting, right? We followed the same methodology which the CIC-IDS was doing, and then we used different type of learning models and demonstrate that if we validate on our campus data, the F1 score is almost 1. If not 0.9, it's 1.0, right? We do better. So, but then when we try to test the same model that we have trained on the campus setting and try to deploy that on target settings, we observe the performance is really poor, right? And of course, this is kind of like expected because we mimicked what was the problem before, the data set that existed before. We see the same shortcut, the TTL being the shortcut, and the model is learning that shortcut, right? Now, we need to fix this problem. The way we fix this problem is that we refine our intent, that let's not use the same distribution that was used in CI/CD. Let's just change some distribution of how these attackers in benign hosts are distributed, right? Now, doing that change or making that change just required me 10 lines of code of a change, right? And I train it again, and I look at the performance on the campus data, and I see it's really high, right? It makes me suspicious. Now, when we try to deploy that in cloud, we see that the performance is quite poor, right? What it is telling me that it is not behaving or performing as expected, right? So it's not generalizing. Now, I use Trusty and understand how it's making its decision. And I see that there is a new shortcut that is coming up, right? This new shortcut is telling me that, if the backward window weights are less than some threshold, then classify, all malicious or benign, right? What essentially it means is that the way this tool was working was that it was just sending attack traffic with the same connection, same TCP connection. It was making multiple attempts to track, and that was overwhelming the server. And that's what this feature is reflecting, right? This can be a possibility in the real world that maybe the attacker is using the same thing, like same TCP connection and launching multiple attacks there. But that's not always the case, right? So we might not expect a lot of generalizability with this type of approach, right? So we go back, change, and make sure that we make a small change that for every attempt you use a different TCP connection, right? Again, this whole change required me just 20 lines of code change. And I do that, and I get the validation stuff on my campus. And I see that, now things are a bit hard. It's not 1.0, it's not very high, right? And when I deploy that in the cloud setup as well, I see that the two numbers are matching with each other, right? So basically, we now are observing the performance is closer to what we were expecting. We dig in, we look at the decision tree and see that, yes, there are these features that do make sense, that they should be there, like the forward segment size, packet length variance, and so on and so forth. So we didn't see any obvious shortcut, right? It does not mean that there is a guarantee here, right? So I'll be very cautious here that there's no guarantee, there's no formal proof. It is based on our intuitions and domain expertise. Maybe what I'm seeing, somebody else might be seeing it differently, so this does not make sense, right? But our understanding is there is at least no obvious shortcut. And the data that we are using now is much better than what we started before, right? With these iterations. So what I'm trying to convey is that we can address these under-specification issues. I would say there are a lot of low-hanging fruits here right now because most of what we have a lot of problems. So we can fix these under-specification issues by collecting better data with a combination of Netionicon and Trusty together. And what it really means is that generalizable models are now better prepared for production deployments because with this better data, we get generalizable models that are ready for production deployment, and something very, very critical when we talk about self-driving network. So I'm just going to switch a bit of gears here to make sure that we get to the conclusion. So this whole thing is very important for self-driving network, right? I would say we have just scratched the surface, right? Like what we really want versus what we have, even with whatever I'm doing, is a very small attempt among many things that we need to do, right? But there is something which is still, this whole thing is still a bit slow process, right? It requires a domain expertise. It requires us to think about, how do you do feature engineering? How do you train the model and so on and so forth, right? What I think the next frontier is a foundation model. Now, some of you might be aware of what foundation model means. It's foundation model are basically the same thing as what is LLM for natural language processing, right? So it's one model that understands, use self-supervised training methods to figure out, understand the structure of the problem, and which can be then fine-tuned for different type of downstream problems that you have, right? Among many things, foundation model is perfect for networking, right? Because as Casey was also pointing out, we have a lot of data. Most of that is unlabeled, right? So, and also a lot of infrastructures have invested in telemetry solutions, SDN-based telemetry. So there's a lot of data that is sitting out there. Most of it is unlabeled. So that's perfect for foundation model. If we can train a good foundation model, then we can just fine tune that for different tasks that we have. And we don't have to really worry about this feature engineering stuff again and again for every problem that we have. We can expedite the whole process. The data that you have, even with the closed loop machine learning stuff that I'm talking about, it will not be perfect. So it will be sparse and noisy and whatever, but these foundation models might be able to extract more value out of that data, right? And in my opinion, the ability to leverage this abundant telemetry data that is sitting out is going to catalyze innovation and development of production-ready machine learning artifacts, right? But this all sounds very great, right? This is very, very exciting and so on and so forth. But what it really is telling us that there is this promise, but it is also very challenging, right? to really harness the power of this foundation model, you just don't have to think about packet traces. You also have to think about how does that connect with the IDS alerts, different type of application-specific logs, system calls, MIPS, and all those things. And these are all heterogeneous data sets coming from different type of sources. They have different modalities in there. And all this information has to be combined together to make it really work, right? What we have done in recent years is that this is something which I would say is a work in progress, but we had this basic proof of concept which demonstrated the power of foundation model. So we were able to demonstrate that with just 2 million flows, this is a very, very small data set. This is what we could do best with the resources that we had, and 200 million parameters. We were able to demonstrate that there is a lot of generative behavior or emergent powers that can be extracted into the model, right? But I think I'll just take a few minutes to peek into the future, given what this promise is telling us, that if I peer into the future, what I see is that given all the promise, if we can get things right, we can think about offering this trillion plus parameter foundation model for network as a service, right? So that nobody else has to do this whole process again and again and again. We can consolidate our efforts in getting the data and the infrastructure that is needed to train something which is a trillion parameter foundation model, right? And then we can offer that as a service to different enterprises, right? So everybody can do this fine tuning using closed loop stuff that I was talking about for whatever problems you care about. You can use that local fine tuning, but then you can think about offering that as a service. And of course, that is very challenging and a forward-looking problem, which is you have to solve very fundamental research questions if you want to get that goal done. How are you going to embed all this multimodal, multidimensional, sequential telemetry data that is sitting out there? How are you going to explain that now you're not creating another monster, which you don't know how to explain, right? So all the tools that I have developed, I was talking about, do not work for foundation model. I cannot provide semantically meaningful representations of how the model is making decisions. So you need to think about that explainability part as well. And then you also think when I say more data, what does that mean, right? How much data is enough? And what data do we really need to ingest in this whole thing, right? And of course, when we're talking about trillions of parameters and maybe trillions and trillions of packets out there, how are you going to scale the whole thing, right? So this is a scalability disaster or an opportunity. So I think this is where, we have to think about how as a community we are going to consolidate. I'm going to lead the effort at DOE, thanks to Inder, where we're thinking about how we can use the telemetry infrastructure that we have already in place to think about developing these foundation models that work at least for one network, right? And we can then think about how we can offer that as a service to other networks. So I'll skip this slide. And in summary, I just want to say that, my theme of research is that we want to really enable this self-driving network, which I think is the need of the hour given where we are in the society right now. But we are really, really far from where we want to be. What I have been doing is just scratching the tip of the iceberg. There is a lot more that needs to be done. But in this talk, I was talking about Trusty, which is the model explainability framework, NetUnicorn, which is a data collection platform, and Pinio, which is the data collection infrastructure that enables you to collect data from your own infrastructure. And moving forward, I think the next frontier for all of us should be foundation model. If we can get it right, I think that will solve a lot of problems that we've been talking about. So with that, thank you so much for your time.
All right, I guess we have time for one question.
Just a quick one.
Yeah.
So Trustee is based on decision trees and labeled data. Do you have near-term plans to start working on explainability for unsupervised data? Something similar to Trustee at that point?
So Trustee does dive into how it can think about providing explanations for unsupervised models as well. It's non-trivial. So yes, to answer your question briefly, yes, we are working on some issues where we can use Trustee to explain some decisions for the unsupervised as well.
Right. I had another just really quick questions. How can Fabric help? Yeah.
So I think whatever I was talking about. Yes.
Yeah. Okay.
Yes. So I think, exactly.
Yeah,
thank you. So this is where I think, the whole process, one of training this type of machine learning artifacts and providing data, consolidating it, providing all the services, data services, as well as building it and offering it as a service. I think that's where Fabric can be extremely useful. And then I think, this whole thing requires a lot of scaling up, right? Mm-hmm. Sitting at UCSB, it's really, really hard for me to do everything. So we need to build a community around it. And I think Fabric can provide the infrastructure support that we're looking for.
We look forward to doing that.
All right. Thank you. Sorry for exceeding the time limit.
Oh, no problem. Thanks, Arpit.